Hi, welcome back. In this lecture, I would like to describe some application of FEM using vector equation, in particular using edge elements that we have been discussing in the previous lecture. The major application that we are going to look at is to find the eigenfrequency of a rectangular cavity. So the problem that we want to solve is the following. So we have a domain S, and we're going to divide in 2 by 2 elements. So 2 elements in the x direction and 2 elements in the y direction for a total of 4 elements. So what we're going to do is to use the edge elements to compute the eigenfrequency and the eigenmodes for a 2D rectangular cavity. Your assignment, we will ask you to calculate the eigenfrequency and the eigenmodes and to plot them on a circular domain using triangles elements. So pretty much the very same technology that I'm discussing now is also going to apply to your assignment. So the problem that I'm presenting now is rather simplified. So we consider a 2 by 2 element resonator to demonstrate the features of the edge elements. So we start first by discussing the meshing, that is a very important part of the FEM method. So we have, as usual, the 2 most important data structure when looking at meshing using FEM. So we have a first data structure that is relating the element number to the node number. So let's see, for instance, the case of element 1, that is the following. And then we assign the node number. So we are going to have the node number 6, 5, 2, and 3. So remember that different options are possible when building this data structure. However, we always need to put these indices in counterclockwise direction. So we need to get 6 and 5 would be wrong if you take 6 and 3, right? And this is because we saw of a geometrical consideration about the area of the elements that cannot be negative. So this is the first data structure, element to nodes. The second one is the one that relates the node to the coordinate in x and y. So for instance, we have the global index for the node 1, that is the following. This will correspond to an x that is -1 and y that is equal to -1 also. When meshing edge elements, we also have a new data structure that relates the direction of the edge element. So in this case, for instance, we relate the edge to the 2 different nodes. For instance, we take the edge equal to 2, and so in this case is this one, that corresponded to node 5 to 2. So in this case 5 and 2. The element 3 will correspond, for instance, to the node 9 and node 6. So is the following here. So when introducing edge elements, we introduce also the nodes to give the direction of the edge element. So the particular problem that we want to solve in this lecture is the eigenvalue problem. We have been looking at this problem in the finite difference method. So we are going to see how to solve the eigenvalue problem using the finite element method. A particular advantage of FEM when solving eigenvalue problem is that it allows us to calculate the eigenvalues and eigenmodes in rather complicated geometries that are much more difficult to map using the finite difference technique. So the problem we're going to solve is the following. So the boundary in the computational domain is metal. So we are going to impose perfect boundary condition at the boundary. And interior is air, so we are going to consider epsilon and mod 0 corresponding to some dielectric constant corresponding to the air. So the eigenvalue problem is stated as follow. This is the curl equation in the frequency domain. So we have curl of E equal to omega square multiplied by the electric constant multiplied by E. And then we apply preferred boundary condition on the surface. So as we know, we never solve the equation directly when using the FEM, but we solve something that is similar, something that is proxy to this equation, that is the so-called weak form. So what we are going to do is to take an inner product or an integral of this original equation. So this is corresponding to take an average equation. So the weak form of our equation is the following, where we are using this Wi that are also called weight function or a test function. So we're going to have a number of these equation, each one with different testing function, right? So we're going to have, depending on how many edge elements we have, we're going to have different equations, right? So this will correspond to a set of different equations. In the case of Galerkin method, we use a testing function or weighting function that are equal to our interpolation function or basis function that we saw in the case of Cartesian grid in the previous lecture. So one thing we can do is actually to cast this set of equation in a matrix form. So we expand the electric field in the terms of the basis function, and we replace the Wi in the previous slides with the Ni, that the interpolation function. If we cast then this problem in a matrix form, we obtain the following generalized eigenvalue problem. So this is S, that is a matrix. This is also called S for stiffness. And then we are going to have Z, that is our known, equal to K squared, that is our eigenvalue, multiplied by a matrix M, that is our mass matrix, multiplied by Z, that is our unknowns. So we solve this equation here, that is eigenvalue problem, for the eigenvalues K squared and the eigenvector Z equal to Z2, Z4, Z11 and Z12, where these unknowns correspond to the edges in the interior of the cavity, right? So Z2 is the following, Z4 is this one, Z11 is this one, and this is Z12. Taking in account that these are the unknowns values of our problem, and the reason that these edge elements values are given by the boundary condition. Those are 0 because this is a perfect boundary condition problem where the tangential component are 0. So how do we solve this? Well, so the issue here is basically to form this matrix S and this matrix M. So when we have the values for the matrix S and the matrix M, we can solve this equation here by calling the Eigenmatlab function. So what we're going to do in the next few slides is to derive very quickly. The textbook provides much more detail. We're going to derive an expression for this S matrix and M matrix. We are going to form it, and then we are going to call the Eigenmatlab function to obtain these K squared values and the Z values, so the eigenfrequency and the eigen modes. So as I told you, the real issue here is actually how to form and calculate the stiffness and the mass matrices. So the elements in S and M matrices are given by the following expression here. So basically these are integral of the curl of our interpolation function with the inner product of the curl of interpolation function on a different edge. And also M matrix, each element of the matrix can be expressed as inner product, the integral of the inner product of the interpolation function. From the previous lecture, we knows already what are these interpolation basis function in the case of the Cartesian uniform grids. So the indices I and j run over all the edges, right? This edge here internally, except for the one at the boundary. So these are not unknowns of our problem. These are given as a boundary condition. You might wonder why we call stiffness and mass matrices. Well, the reason is that these two matrices are very much in use in mechanical engineering, right? So the stiffness of the material and the mass of the material is very important, are very important parameters, right? So we borrow these terms from mechanical engineering, right? So we retain the name, even though when it comes to electromagnetic field, they don't have a very strong physical meaning. So this is a procedure, so we can calculate this integral. We know n, by just a geometrical consideration, we can calculate this as ij. Of course, what we can do is to apply a technique that we've been using in the FEM when solving the scalar equation. So instead of calculating directly the integral all over the domain, what we're going to do is to calculate that integral for one element and then sum it up all the elements to calculate the global matrix by using a procedure called assembly procedure. So for a realistic case, we do not evaluate directly as ij and mij using the expression from the previous slide. What we do is something more convenient, that is to use the assembly procedure we saw in the case of a scalar equation with FEM. So what we do, we evaluate the element matrices Sij of the element E and Mij of the element E. And here we basically have these simpler integrals to the integrals in the specific element. So by geometrical consideration, we can calculate these two matrices in the following way. So we exploit the expression for the basis function, and also we use knowledge about the corresponding local numbering and reference direction of the edges given for an arbitrary element E. So these two elemental matrices entries are calculated as the following. This can be calculated by just some geometrical consideration. So we have the matrix SE, basically using Lx of the element E and Ly of element E. So Lx and Ly adjust depending on the coordinate of the element. So as we saw in the scalar case, we just need information about the coordinate of our element. So this is the expression for S, and this is another expression from the matrix, the elemental mass matrix, right? So we have this matrix here that is multiplied by Lx and Ly of E divided by 6. The assembly procedure gives the global matrices, that is basically the sum of all the elemental matrices. One thing we need to note is that if one of the two edges is reversed between the local and the global ordering, then the sign of the corresponding row and the columns in the element matrix must be changed before it's added to the global matrices. So if this happens here, instead of having a plus, we are going to have a minus. So in this case, what we do, we calculate the elemental matrix for element 1, element 2, element 3, and element 4. And then we basically sum it up, right? Obtaining the global stiffness matrices from all the assembly procedure of the elements. So here, these are the one, and then in the square bracket, we put which element is give the contribution. So this entry here, we take one from here and one from here. So it's one and one from the first element and one from the second element. The very same can be done for the mass matrix assembly. So we have 4 elements. we use the expression we shown in the previous slides, and then we basically sum it up. This results in the diagonal matrices. So just putting everything together, what we have in our 2x2 resonator, Cartesian resonator, rectangular, is the following. So we have the global matrix S and the global axis M, and then we have the Z that are the eigenvector. So here we have Z, and here that is deleting in this slide is also we have Z, and then K square are the eigenvalue. So what we want at this point, once we have the matrix S and the matrix M, we can just call the MATLAB function to calculate this K square and the different component of the eigenvectors. So the most difficult part is to form this S matrix and M matrix, and then we use MATLAB to calculate the eigenvalues and the eigenvectors. So the first thing when we want to solve this is to form our matrix S and M. I used the expression from the previous two slides, so we know that S is this matrix here, and then we know that the mass matrix is this matrix here. So we just write the matrix, the stiffness matrix and the mass matrix. At this point, then we use the generalized eigenvalue solver in MATLAB. That is, we provide Eig, and then the stiffness matrix and the mass matrix, and we obtain two major values. So we obtain V and D. So D is the diagonal matrix that has the eigenvalues on the main diagonal. So in this case, we will find the eigenvalues equal to 0, 3. So this is the generate eigenvalues, and 6. Also, we have the eigenvector corresponding to these eigenvalues stored as a column in the matrix V. So this is going to be one eigenvector, second eigenvector, third and fourth eigenvector. So these eigenvectors are not normalized, so they are orthogonal but are not normalized. That means that the magnitude of this vector is not 1. So we need an extra step, and to calculate we need to normalize this eigenvector. So what we do, we take these vectors, and then we divide by the module of each column. That is so that the magnitude will be 1. So if we do that, so for instance, I did the normalization, and this is the case, and you see that is minus 1/2, 1/2, and minus 1/2, and so on and so forth. So in your assignment, we will ask you to do the same procedure. So we provide a code to calculate the matrix S and M. Then you will need to use the generalized eigenvalue solver in MATLAB to derive the eigenvalues and the corresponding eigenvectors, and then you're going to normalize, and as final step you're going to plot the values of these eigenvectors. So you're going to do in a rather difficult configuration, that is a circular configuration using triangular elements. So the expression for the matrix S and M will be different. They will describe quite thoroughly in the textbook, so I strongly suggest you to look at those. So this is the last slide, and talk to you soon.